So let's look at the rate of a chemical reaction. And when we have a chemical reaction, sometimes these reactions are slow and sometimes they are fast. And depending on the type of reaction we have, the speed or the rate is very, very important. So if we had a car, for example, we want that car to rust very, very slow. We don't want that car to rust in weeks or months. We want it to last 10, 20, 30 years before it'll rust out. Whereas a reaction we want to be really fast is something like lighting a match. Matchstick, that chemical reaction, we want it to occur right away, almost instantaneously. We don't want to wait 2 days, 2 minutes, 2 hours. It doesn't matter how long. We don't want to wait. We want that matchstick to burn right away. So the reaction rate is really just the amount of a reactant either consumed, how much is used up, or the amount of product formed per unit time. So if we're using that car example, the reaction rate might be the amount of iron that's used up or the amount of rust that is created. And when we're talking reaction rate, we're really just talking about the speed of the reaction, how fast or slow that reaction is. Now, when we are measuring reaction rate, we can measure it in a variety of ways. We may talk about the reaction rate in terms of the mass of something that is reacted. How much is actually used up? Now, that would be one way to calculate reaction rate. We could also, instead of mass, calculate in terms of volume that's either used up or produced, how much is created. Now notice whenever we're talking about reaction rate though, we're always concerned about time. We're always going to be measuring the time of a reaction to determine the actual reaction rate. So let's look at a situation. Zinc combined with hydrogen chloride. We get 2,000 cubic centimeters of hydrogen in 12 minutes. We want to find the actual reaction rate. Well, here's our formula we can use. The volume of hydrogen gas produced divided by the reaction time. And then it's just a matter of using what we have. And in this situation, we have 2,000 cubic centimeters of gas, and we're dividing it by our time of 12 minutes. And then we can find our reaction rate, and we can find that reaction rate in terms of minutes or seconds. We just put 2,000 divided by 12 in your calculator, and if we were rounding this, we would get 166.7 cubic centimeters per minute. And again, we could change that reaction rate to whatever time we like, but there's our amount that's produced per minute. There's the rate of our reaction. Well, let's look at reaction rate in a little more detail here. Now, before we do, there's a couple theories we need to know. First one is what's called the kinetic molecular theory. And kinetic molecular theory is a pretty simple theory that says that all matter is made up of tiny moving particles. These tiny molecules that are constantly moving, that's where we say kinetic, they're constantly moving around. When we want to have a chemical reaction, we also have to consider what's called the collision theory. And the collision theory tells us that molecules must collide in order to react. So these tiny moving particles must come together, crash into each other, and collide. And the reaction rate comes from this collision theory, because in order for collisions to be effective, and when we say effective, what we mean is in order for there to be enough energy for a reaction to occur, we must have collisions that are effective, that really have sufficient energy in order to react. So let's look at this in terms of a picture here. Imagine if we had hydrogen and iodine. These two molecules, they're just out floating around doing nothing, and hydrogen comes along and it crashes into iodine, but there's hardly any collision, there's hardly any energy, and really they just bounce into each other and then bounce right off. There's absolutely no reaction because we have what's called a dead collision. They don't react. Not enough speed, not enough movement. But if we could somehow take this collision and take these two molecules and get them to collide faster. Get them to have more energy, more movement. So they're going to come in really fast. And when they crash together, they're going to have an effective collision. And notice what the effective collision does. It essentially breaks apart the H2 and the I2, and then they combine with each other. And we get HI and HI. We have a new product that is formed. And so we want to try and determine what controls this effective collision. And to make these effective collision, what we have to do is we have to change the frequency. And frequency is just the number of collisions. If we can increase the number of collisions, we can change the reaction rate. And by changing the frequency, we actually are able to change the speed of the reaction. Now, how do we do this? Well, there's 4 ways that we can actually increase the reaction rate. The first one is increase the concentration. If we are able to have more reactants, we are going to have more collisions, and this is going to cause an increase in frequency and will increase the reactant rate. We could also take the surface area and try and increase the surface area. So we can take something that is a solid and make it a powder. What that does is it gives more places for collisions to occur. Well, that's 2. There's a couple more. Probably familiar with this one. Increase the heat. Turn up the temperature. If we increase the temperature, the particles start moving faster. And if we have 2 things moving faster, the collisions will have more energy, and we'll have more collisions, and we can increase the reaction rate. And our last one is by adding what's called a catalyst. And a catalyst is a substance that we add to a reaction. It is not used in the reaction in any way, but what it does is it really provides a shortcut, a way for the reaction to occur with lower energy. And we're going to look at catalysts in more detail, but this lower energy allows more effective collisions to occur. Now, when we are increasing the reaction rate by using these 4 methods, we can also decrease the reaction rate by going backwards. Remove a catalyst, decrease the temperature, decrease the surface area, decrease the concentration. So when we're talking about rates of chemical reaction, we must remember that it's not only going forward, it's also going backwards, increasing or decreasing. Now, if you do go on and do more advanced science, you're going to talk about enzymes, especially in biology. And an enzyme is really just a catalyst within a living organism. And enzymes can occur in your body, particularly in your organs, such as the liver, that causes a chemical reaction to occur, but an enzyme is really just a catalyst living within an organism. And that actually takes us to the end of chemistry in Science 10.